Okay, so this one. Okay, so there is this number one problem is this, and let me read number two. Assume that all transmission lines are made of 50 ohm microns, they're printable silicon. Okay, assume the conductor lines are made of copper. Find the total power loss across the transmission line and across the loss along the stub. Okay. If you want to see how this problem will be solved, can be solved, you need to look at some of the review examples that I incorporated. Let me find it. 1 second. No. Okay, I will go there. Go here. So today just 1 second. Come in. I have office hours after 4. Yeah, thank you. So 1 second here. All right, so you go to modules, you will see there is one after 3 that is called Review on Transmission Lines. And you will find out that there are a lot of examples with matching networks. So let me see on this one. So that's 1/4 of a wavelength. That's one matching network with a series stub. All right. So it shows how to do that, and by using the Smith chart. Also, there is one with a shunt stub. Also, it shows that on the Smith chart. And then if I leave that and go down, example 1. Okay, that's also something very similar that we have, even if this is series, but you have to do it with shunt stub. And this is solved both analytically. Well, let me see, I think it's solved only analytically. But if you go with a Smith chart here, now this is one, very similar to what you have to solve. So if you go to this problem, you're going to find out how to solve it, all right? But I will do one more as an example to see how to do it. But I would say you go to this problem to see how to solve your homework. So I will go quickly over this one, and then I will focus more on how to go about looking at the second problem. And then I would like to see if you have any questions for me, all right? So let me go away from this for a moment, and I will go back to, in fact, I will do it from here, since we have. Oh, sorry, I'm sharing. Sorry, the only thing I can do is from here. All right, so assignments. Okay, so that is a section of line, and it says, consider a 50 ohm source with 2 volts, internal, 2 volt, 50 ohm means the internal impedance 50 ohms, that is connected to 50 ohm transmission line And then it gives you a load in admittance and say, identify all critical lengths as a function of the design lambda. Assume that, so in this one, identify all critical lengths as a function of the design wavelength lambda. Assume that L is 1.5 lambda when the design frequency is omega naught to pi f naught. Okay, so first of all, this one, for some reason, number 2 has to be after number 1. For some reason, I don't know even why I moved up. But design a shunt stub that will be placed somewhere in the transmission line so that we have maximum power transfer to the load. Make this design by using the Smith chart. And then number 2 is to identify the critical lengths. And number three is using the Smith chart, find the reflection coefficient. Okay, so what I will do is that I will solve a problem using the Smith chart practically. So I'm gonna go, well, I'm gonna do 2 things. Let me see, I'm gonna go and find a good Smith chart first of all. And go to the modules. I'll go to Smith charts. And I think this is the best one to use. So I will, how do I copy it? Ah, here. I'll put it in Notability. Create a new note. And I will put it in homework 3. Okay. All right, so we have that. So now we can go to Notability. There. Okay, so I'll solve a different problem, but I will do it on the Smith chart so you can see how to do this one. So let me close this one. Go to homework 3. Okay, so I will do a new note. A second. Okay, so let's assume this is problem solving session, another problem solving session. I think I cannot write up there. Okay. Anyway, I will clean this up later. So, all right. Example. Consider the following. Transmission line network. All right, so here I have maybe I'm using this. So all right, I don't know. Okay. This is our network, but in here, so we have 2 transmission lines. This one, this one. So one transmission line is here. And duplicate here, and is connected to a load all right, so this load here is ZL equal to say 100 plus J 150 ohms. Okay, assume that this transmission line is 50 ohms. And then on the other side is connected with the source, which has an internal impedance of 50 ohms. And then it's 50 ohms. And the source has 1 volt. Let me see. Okay, that's Vs. And let's assume that Vs is 1 volt. All right, and we now, this is a network, but what we want to do in this network, support obviously, is using a stub, using a shunt stub design the network so that matches. So we have okay, so that we have maximum transfer of power to the load. Assume that the design frequency have not to be 10 gigahertz. Okay, and also assume that this length L and L equal 3 centimeters. So I give you the length in physical dimensions. All right, so find the location of the shunt stub and calculate its length, all dimensions in centimeters. Okay. So this is 1, 2, also 3. Assume that both transmission line and stub are made of ideal transmission lines, ideal and lossless transmission lines, and the stub has a characteristic impedance of 50 ohms. Okay, so that's the problem. So let me redo this problem, the schematic, to see what we have to find. So obviously, we will have to place a stub, shunt stub, somewhere on this line. There is one more thing, restriction, but in any case, before I get there, we have to place the stub somewhere on this line. We don't know where, but we have to find exactly its location, and we will have to find its length. It's a shunt stub. We don't know whether it's open or short yet. However, I'm giving you an additional condition here that says use the shortest possible length for the stub, possible length for the stub. Okay. So now here we are doing the following. We assume that we are going to place the stub somewhere on the along the line. So the line is going to be this one. We're going to, let's assume that somewhere between one, this is one section of the line. This is the other section of the line. And let's assume somewhere in between, we're going to place that stub. It's going to be shunt. There. Here. And let's assume that the stub, I'll use this color, but I will do it like this first of all, and then like this. And since there is going to be a transmission line, let me see, I'll go here. Okay, so work here and here. And then we don't know whether it's open or short, but what we know is that this characteristic impedance is 50 ohms. 50. We know that this characteristic impedance is 50 ohms. We know that this characteristic impedance is 50 ohms. And then we know that here we connect it to the load. ZL. And we know that the total length of this section is L. L, and we said this is going to be 3 centimeters. We know that the source is somewhere here, and is 1 volt, I believe I said it's 1 volt. So Vs 1 volt, and we know this is 50 ohms. That's Zs. So this is Zs, and the source, and this one is the load. And the load is complex. So I have given for it 100 plus Ju150. So let me write it here. Now, how are we starting to solve this problem? First of all, we are going to normalize everything to 50 ohms because all of the transmission lines are 50. So we'll normalize all of the impedances to 50 ohms. So we have, so number 1, normalize ZL to 50 ohms. Okay. The other thing I wanted also to show is like that I would like to call the length of the stub d sub s. So this one is d sub s. All right. And then here that can be open or short. Open or short. All right. If we normalize ZL to 50 ohms, it becomes normalized equal to 2 plus J3. All right. Now what we want to find is D sub s, and then also we want to find this length here that will tell us exactly the location. So this length, let's call it L stub, the location of the stub, and ds is the length of the stub. All right. Now, how we're gonna do this? We're gonna, first of all, since we have a shunt stub, always, this is, if we have a shunt stub, we work with admittances. If we have a series stub, we work with impedances. So here we have number 2. So for some stubs, we work with admittances. And so that we highlight to remember it. Which means that Z sub L has to change to an admittance. So Z sub L normalized has to change an admittance. There are 2 ways to do it. Okay, so way 1 is to do it through like using numbers, complex numbers. One is to say ZL is 1 over YL, which implies that YL has to be 2 minus J3, excuse me, 1 over minus 1, I did it anyways, 1 over 2 plus J3, which implies YL we have to multiply numerator and denominator by the complex conjugate of the denominator. So it's 2 minus j3 divided by 4 plus 9, which is 2 minus j3 divided by 13. And let's see how much that is. Right. Is 2 divided by 13.154 minus j 3 divided by 13. This is 0.23. So YL is 0.154 minus j 0.23 normalized. The other approach is to find it using the Smith chart. 3. So find YL, which is the inverse of ZL, using the Smith chart. Okay, so now we're going to do that. Let's see, we have a Smith chart here. I'm going to copy it, go to here and paste. All right, but we're going to make it bigger. All right, how do we find? So let's also do that. First of all, number one, find YL. How do we do that? First of all, we place on the Smith chart Vswr normalized. Vswr normalized is is here 2 plus j3. So 2 real part plus j3 imaginary. So the real are always circles that have their center on the real axis and are tangential to the Smith chart on the right. Let me just do it again so it makes it a better circle. So now that I cannot do that. So here. And since all of these are the resistance circles, meaning all the points on these circles go through the constant resistance circle. So all the points of these red circles have resistance normalized, which is 2. And then the other one, we said it was 3. So we go to find 3, positive 3 for reactance. All the reactances are up here, somewhere there. And then if I find 3 ups, that 3 is right here. And I write this circle. And I find a cross section between the green and the red. And this one is ZL, normalized. Now, to find the admittance, I'm writing the circle that is called the constant Vswr circle, and is the one that has as a center, the center of the Smith chart, and it goes through this point. Let me just write it. By being on this circle, practically, by moving on this circle, practically you move along the transmission line. Okay, approximately. So now we draw the line from this point, which is ZL. We draw a diagonal line, I mean the diameter, I should say, of this purple circle until we find the anti-diametric point, which is down here. It's here. And that's that point there is nothing else but the admittance that corresponds, the normalized admittance that corresponds to the normalized impedance. Now let's see whether what we found is correct. So if we go and read here, the red circle that goes through this point is this one, approximately, and the reactive circle that goes through this point is this one. So this point is the cross section of the red. In fact, I could make the red bigger. Oops. Make the red bigger. Okay, make it bigger. Okay, I'll correct it. And there. So it's higher. It's there. Okay. That's the circle that goes along the line. Let me see. There. But okay. So that one, if we want to read it, is somewhere here. And that is 0.1. It's 1, 2, 3, 4, 5, 6, 7. 0.17. So y Isabel here equals 0.17 minus j, and that here is 0.2 minus 0.222. Okay, let's see how much we found it. Okay, very close, 0.23 here I found, and the other one I found 0.17, it was 1.54. I guess I did not read it very carefully, or the point that I put it is not very carefully, but that's how you find the approximately the normalized admittance. So using the Smith chart. Now that we have the normalized admittance, I will try to find the matching network. So find stub location and length. Okay, now I'm gonna get another, copy this. I'm gonna put it here, paste, but I'm gonna clean it. All right, so all this. And I'm gonna only use the value of the admittance, the found, which is it's 0.17. I'll use that one. It's 0.17123. Here, 0.17. And the resistive circle, 0.1, 2, 3, 4, 5, 6, 7. I don't write the whole circle. And then it's 0.22 down here. See? Okay, so that is y sub s. Okay, so y sub s. Y sub s, excuse me. So now I'm gonna move along the transmission line from the load towards the point where I have to put the stub. And to do that, I will move along the circle, the purple circle that has its center at the center of the chart and goes through the YL point. So let me do it like this. Okay, like this. Okay, a little bit inwards. Okay, so now I will have to move towards the generator, which is here. Oops. So I have to move along this direction from the point where I am, and I have to move until I find the circle whose real part is 1, which is this one. Okay. So I'm going to move from there. The question is, why do I select this circle? Why did I select the circle who has a real part equal to 1? Can anybody tell me? Who can tell me? Okay. Why do I do this? Who's gonna be able to tell me? Well, we do that because after you add the stub, when you come after you are here, all right, so after at this point, if you have been able to create a perfect match, the total admittance here, input, is gonna be normalized. The real part is gonna be equal, normalized is gonna be equal to 1, normalized with respect to y naught. So we need to find the circle that has a normalized part equal to 1. There are 2 points on this circle. So I can either go like this or extend point A or continue my journey and go to point B. All right, I can continue and I can use a different color, like a lighter one, or I can continue here. I go to point B. Then from there, I will have to go to the center of the chart. And I will be able to go to the center of the chart only here. Let me use a different color because it's not easy to see. This. I can only go to the center of the chart if when I am at point A, I can come down this way. Which means I will have to remove an reactive part. So the stub needs to have a negative input admittance. Or if I come down to part B, I will have to walk upwards. And I can go like here. There are 2 options, therefore. So, and this is the center of the Smith chart. Let's call that point C. So from A to C, that one gives us one solution for the problem, which is going to be, in fact, I'm not going to do this here, but I will say this here and this, the distance between these 2 points gives me YL1, while this one here, this distance will give me YL2, all right? But in one case, I have to travel from my YL point to A, the other I have to travel to B. So I have 2 different possibilities. So let's see how many possibilities I have here. All right, so let me call this point, how much should I call this? Point L. Okay, so I call it L is the load. So from L, point L to A is going to give us a length L sub S 1, L sub S 1, which is the first solution. And the length in this one, to find it, I have to connect the center to this, and then I will do this also like that, and then I will have to find, I need to find the distance, so I will have to go here and look at where I am here, and then I will have to connect this to this, right? Then make that also, and then look at this and see how far I have to go. So this point here is 0.464 lambda, and this point here is 0.1819 rather, 19 lambda, and therefore LS1 is going to be 0.19. I'm going from 0.464 to 0.5. So the distance, this is 0.5. So the distance okay, so here it's 0.9, 1 second. Oops. Okay, so it's 0.19 minus, and then the distance from here to 0.5, right, is 0.5 minus 0.464, and that's lambda. So practically, let me see how much this is. It's 0.19 minus 0.5, that's 0.464. It's 0.154. This is 0.154 lambda. Okay, so that is, let me write it here. One solution, therefore, we found is that LS1 is 0.154 lambda. And that is when we stop at point A. At A. Now, if we stopped at point B, then we will have to draw this line here. And then we will have to find the additional distance we went from. So practically, we are now, instead of 0.19, now we stop at this point, which is 0.31. So practically, LS2 will be 0.31 minus 0.5 minus 0.464 lambda which is gonna be 0.31 minus 0.5 plus 0.464, which is 0.274. It's LS2 is 0.274 lambda. So we found at point B. Now, in the first solution, LS1, we need a YS for the stub to be equal so that 2 minus J, we need to, in fact, we have the following. At the point where we place the stub, okay, we will have that Y in at that point is going to be Y sub S, which is the stub, plus whatever impedance we had from the line, all right? So in fact, input at some point. So if I go here and I call this A, no, I don't want that A. So A is here where we have the load. Now A is, okay, I call this A here and AA prime here, right? So this one, if we put the stub there, is the input impedance, Y input, is going to be equal to YS plus Y input at AA prime, whatever comes from the line. Okay, so to be able to go from this one here, well, I need to, so I don't get you too confused, from here, then from AA prime. So from here, we find that Y input, which we want it to be 1, gives us eventually that YS is going to be 1 minus Y input at AA prime. And if you put the value of 1 input at AA prime, which is 1, okay, so it's on the circle that has normalized resistive part 1, so it's 1 minus 1, and then minus J Y for the stub. So practically, in fact, we should not use the same Y here. Let's call this X. Let's call it YX, okay, for the stub, which implies that XS normalized is going to be minus for the stub, whatever the reactive part is here, that is from C to A, which practically it's going to be, A is close to 2, all right? So it's going to be minus approximately 2, all right? And in this second case, where now we are at point B, 274 lambda, we have that from point B, we have to go up to C to 1. So in that case, X sub S for the stub has to be 2, normalized. All right, so on the basis of that, we're going to find 2 possibilities for the stub, how long it should be. Both of these solutions are possible, practically. You don't necessarily have to find all of them. I want only one set that is correct. All right, I don't necessarily need both, even if I solve for both of them. So for now, let's go with the first solution. So solution number 1. Okay. What I will do, I will use another, so I can keep it clean, copy, go here, paste, and then I will clean it. Okay. So let's now work for solution number 1, which says that the stub has to be -2 reactants for the reactive part of the admittance. And -2 is here, -2 is down here, down, -2 is down here. Now, we have always to move in this direction. If the stub is open, meaning infinite impedance, its admittance is 0. So for an open stub, open shunt stub, the load, the end at the end of the stub, Z sub L, if it's open, is infinite, but Y sub L, excuse me, let me say, Z sub S L is infinite, normalized, but Y sub L S L is 0. So it's going to start here for an open. For a short end, meaning shorted at the end, shunt stub, it means that ZSL is going to be 0, or YSL is going to be infinite. In fact, that is here. That's solution 2. And for solution 1, in terms of Y, we are here. All right, that's solution 1. So we see if it's like solution 1, if it's open stub, so open-ended, we have to start here, move all the way around this, go through this point, and then come down here. But this distance is longer than the distance we would go if the stub were to be shorted. So if the stub was shorted, like in solution 2, we will only go from here down there, which is a much shorter distance. So we are going with this one. And for this one, we find that D sub S for solution 1 is going to be from 0.25, we have to go all the way starting from here. Okay, that's 0.25 there. So let me write it. This is 0.25 lambda, and this is here 0.324 lambda. So the distance between these two is going to give us this abyss 1, and this abyss 1 is going to be 0.324 minus 0.25 lambda, which is 4, in fact, 9, 9, 9, 9. No, sorry, don't know what I'm doing. It's 4, 7, lambda. Okay, so ds1 in this case is 0.074 lambda. And you can do, you can go for solution 2, which is 2x up here. So solution 2, this is solution 1, open or short. For, you can do a similar thing for this one too. And copy, paste. So if this is 4 and 2, point 274, 0.274 lambda, when x is 2. X is 2, that implies, let me erase a few things. Okay, that implies that we are here and we have to go there either from this point or from this point, all around go, this way. This way, up until we come here. Or go from here all around until we go to this point here, like we did last time. So we are gonna, the only possible solution we're gonna get is this one. All right, to find that distance, take this line, no, this, and we find this number here. And obviously in this case it's for open, so it's for L1, it's for the open case, so it's open. So this one was for short stub. Okay, and this one is for open. And this abyss in this case is gonna be 0.177 lambda. So these are the two possible solutions. For open-ended stub, we have this. For shorted shunt stub, we have this. Okay, and then practically from there, you can find the physical lengths. And we find lambda, but lambda naught we said was 3 in 10 gigahertz is 1 centimeter. Oh, well, excuse me, 3 centimeters. So we can then translate all lengths into wavelengths. Excuse me, translate all wavelengths into lengths, into centimeters. So that's what we have. That's how you would solve this problem that you have. I have done it very extensively, but it's also, as I told you earlier, in one of the problems that we have in the review section. And the only other thing that homework 3 has is that it asks you to calculate the loss in dBs as a function of frequency. So the best way to do that, it says that your loss is gonna be only along the line. So practically, you would have to find on this line, L, you have to find the total attenuation constant. You need to remember that on, let me go into the solution. My notes, all right. So if your line, so that's the second part. If your line has losses, low losses, obviously. So from the data I give you, you find alpha. And what I give you is tangent delta, which in fact, according to the problem, let me see, tangent delta is 0.008. And I give you also the function here. Tangent delta is 0.008. And so the attenuation constant, so the dielectric has a dielectric constant which I'm giving you. So you plug in loss tangent delta, you have it as a function of frequency. And you find the attenuation constant. And there is also a skin depth. If you go to the web, and then you say that you need copper with a skin depth of 0.7 micrometers at the design frequency, practically you're going to find out how much is your conductor losses. And you will find the conductor losses, in fact, from the tables for copper. And then, so you will have that now we go back. So after you find your total losses in the line, so from tangent delta, you find A, which are the losses of the dielectric. And then from skin depth, you find also the losses due to conductor. And so the total loss is going to be A dielectric plus A conductor. So I have called that in the notes A. So it's going to be A plus A sub C, the total. And then you know that your V is plus E to the minus, excuse me, here. So your V plus, if you have a line that is matched, practically you're going to have an input wave, all right? So that is going to give you a V to be equal to V naught E, this V plus, to the minus J beta L E to the minus A L, and your I plus is going to be I naught E to the minus J beta L E to the minus A L, and then P, which is V plus I plus complex conjugate in 1/2. Then this is going to be equal to V naught plus I naught plus complex conjugate E to the minus 2AL. So practically, if at L equals 0 in the beginning, all right, where L equals 0, P, what is coming in the line, the P incident, is going to be equal to 1/2 V naught plus I naught plus complex conjugate, which is practically the initial power from the source. Power from the source. But at L equals the length of the line, which is primarily the longest, all right, because in all cases, the length of from on the line from the stub is really a very small fraction of the wavelength. So practically at the end of the line, you're going to have a P at the load, which is going to be 1/2 V naught plus I naught plus complex conjugate, but times E to the minus 2AL. And therefore, what you're going to lose between the two is P in, the amount of loss in the power is P in minus PL. If you want to find it in percentage of the initial power, which is going to give you 1 minus E to the minus 2AL. And that's in fact your loss in power in terms of percentage of the initial power loss. So that's how you're going to solve this problem. Okay, with that, I would like to stop and see if you have any questions. Do you have any questions? Okay, if there are no questions, then I will upload this as a part of the problem solving session, and I will also upload the video. Okay. So I will see you later.
Thank you.
All right, bye-bye.
Bye.
Come in. Hi.
Have a nice office.
Thank you. Thank you. Can I make a very brief phone call?
Yeah, you can.
Okay. Thank you. Thank you very much. Έλα, κορίτσι μου, τι κάνετε?
He's here.
Όχι. Πού είναι το Δινάκι? Θα τη είδα.
Here.
Καλά στο μου. Καλά στο μου, όμορφο κουκλίτσι μου. Τι κάνει καλό αυτό?
Nina has put us through the past 24 hours.
Γιατί, τι έκανε?
Okay. Literally 1 hour before she's supposed to go to daycare.